In this lecture, we have an example where we apply the LU decomposition to solve the matrix system of equations A times x equals b, where A is given by this tridiagonal matrix and b is this constant vector. X is the vector of 5 unknowns, x sub 1, x sub 2, x sub 3, x sub 4, and x sub 5. We assume that A can be written as the product of a lower triangular matrix L and an upper triangular matrix U. We are also assuming that the main diagonal of U is composed of ones. Then the components L sub ij and U sub ij of L and U respectively, at least the non-zero ones, are given by these formulas. It is worth noting that when I equals j, U sub ij or U sub ii ends up being 1 under this formula for U sub ij. We replace A by L times U and rewrite the matrix system as L times U times x equals b. Let U times x be the vector y with components lowercase y sub I. We further rewrite the system as L times y equals b. Then the y sub i's are given by this recursive formula. And the x sub i's are given by this reverse recursion. We are going to use the software Mathematica for this exercise. We first input the matrix A. We start with a pair of curly brackets. Each row of A is enclosed in a pair of curly brackets nested inside the main pair. The first row of A is 2, 1, 0, 0, 0. The second row of A is 1, 2, 1, 0, 0. And we continue to input the other rows. We input the column vector B. B, like A, is a matrix, so we use nested brackets. Let n be the number of rows of A, so n equals 5. We enter the formulas for the entries of L and U. For this, we use a do loop. Inside this do loop is a pair of nested do loops, one for the entries of L and another for the entries of U. For the entries of the L matrix, since lowercase l might be confused with the number 1, instead of lowercase l, we'll designate the entries of the L matrix by double L. The first term on the right side is the entry A sub ij of the A matrix. We use uppercase A since we are using uppercase A for the coefficient matrix in the code. Then we have double brackets for the entries of the matrix. We are using double brackets for the entries of A because we are extracting the entries of A from our definition of A within the code. Inside the double brackets are the row number I and the column number j. Double L sub ij equals A sub ij minus the sum of double L sub ik times U sub kj. For the summation, k goes from 1 to j minus 1. For this first inner do loop, the one for double L sub ij, j goes from 1 to I. Then there's the formula for the second inner do loop, for the entries of the U matrix. Let's examine the formula for U sub ij. Having j start at I should also cover the diagonal entries of U, and these we already know are all equal to 1, so there is no need to calculate these entries. And we should point out that part of the reason that we still talk about a method like LU decomposition is to speed up algorithms by reducing the number of operations, specifically the number of multiplications and/or divisions in algorithms. Now, if j starts at I for the U sub ij's, the do loop will add unnecessary multiplications and/or divisions to the algorithm in computing the diagonal entries, which we already know are all equal to 1. So we modify the formula for U sub ij. We include an if-then-else statement in the definition of the U sub ij's. If j double equals I for the entries on the main diagonal, U sub ij equals 1. Otherwise, we calculate U sub ij using this formula. If j is not equal to I, u sub ij equals the quantity a sub ij minus the sum of double L sub ik times u sub kj. For the summation, k goes from 1 to I minus 1. We divide this entire quantity by double L sub I. Since j is at least as big as I, j goes from I to n. For the main do loop, I goes from 1 to n. We define the L matrix using nested tables. The inner table is for the entries of each row. These are double L sub ij, where j goes from 1 to n. For the outer table, which is for the rows, I goes from 1 to n. We do the same for the U matrix. We simply copy the code for the L matrix, paste it, and change double L to lowercase u. We execute the entire code. Here are the components of L, and here are the components of U. We can view L and U this time in matrix form by typing L / matrix form and U / matrix form and evaluate the entire code. These are the zeros above the main diagonal of L. Like the ones on the main diagonal of U, we don't need to calculate these. These entries are the zeros below the main diagonal of U. We simply ignore them. We'll tidy up the screen for future calculations, so we delete these lines. To solve for the vector y, we use another do loop. We have y sub I. Then we have to extract the entries of b, so we use double brackets. We have row I and only one column since b is a column vector. From b sub I, we subtract this sum, the sum of double L sub ik times y sub k. The summation has k going from 1 to I minus 1. And then we divide by double L sub I. For the do loop, I goes from 1 to n. To get an on-screen output of the y sub i's, we also type table y sub I going from 1 to n. To generate the x sub i's, we use another do loop. X sub I equals y sub I minus the sum of u sub ik times x sub k. The summation has k going from I plus 1 to n. We must remember now that it is a reverse recursion for the x sub i's, where the index I starts at n and goes down to 1. So for the counter for the do loop, we type I, comma n, so that I starts at n, comma 1, comma minus 1. This minus 1 instructs the do loop to decrease I by 1 at each step. For the on-screen output of the x sub i's, we apply the table command. I goes from 1 to n, and we execute the code. These are the y sub i's, and these are x sub 1, x sub 2, x sub 3, x sub 4, and x sub 5.